So basically the idea is that we go through 3 projects. Each project gives a little presentation of a couple of slides presenting what they did. And then our independent judge, Terry, who might not be so independent anymore now, picks an object that each of us needs to evaluate on. And then each of us shows how their setup does on this object, and we see who actually gets it right. If we have a tie, we'll have to pick another object until we have a clear winner.
Can go all night.
And so that's half of the points you can get. And then the other half of the points are rated by our independent judge, Terry.
Oh gosh, a lot of pressure here for me.
Yeah, everything rests upon you now.
Oh gosh.
So there are a couple of different categories. And Terry, if you feel like uncomfortable rating on any of these, don't feel like you can skip it. But basically, you just put an X in the column of which team you think did best on that. If you think there's a tie, you can put 2 X's, or just nothing if none of us did good in it. And so the categories are best in show / most fun presentation, easy on the eyes, so the most beautiful setup, impressiveness of the solution, the most ambitious project, the most creative solution when encountering issues, team players, so a team where everyone contributed really uniquely with their skill set and you collaborated very well, best demonstration of Monty's capabilities, and made you most excited about Monty's future. And then the last item is rated by all of us. So basically, each of us will put 1 X into one of these columns, and we count them up. Basically, you say, this team helped us the most. You can't put it into your own column, obviously. Does that all make sense?
So it's not going to be blind then?
No.
No.
Okay.
You worried that people will get mad at you because of your judgments?
No. I'm okay with me. So can you tell me, I know that It's Not a Tumor is the international team. Everything is Awesome is whose team?
That's Rami. That's the Lego team.
Okay, that's the Lego team. And the other ones, okay.
Yeah.
So I think the only two, the main two that I feel uncomfortable with is because I don't know enough about Monty, is the 2 that mentioned Monty.
These 2?
Yeah.
Yeah, so with this one, you could just think of like which one you feel like shows the most promise, or you feel like this might be something really cool in the future, since those are all just demos. But
Okay.
if you don't feel comfortable after the presentations, you can just leave the row blank.
Okay. And this spreadsheet is where?
I'll send you the link again.
Link. Okay.
I'll send it to you on Slack.
All right. I have to take notes. I haven't taken notes in years.
Well, it's not that high pressure. All right. So are all of you guys ready? Do we have a volunteer for who wants to present first? Does Terry have to pick someone?
Oh gosh, so much pressure here. Okay, so
and yeah, so with the presentations, try to keep it under 10 minutes if you can.
Yeah, so Icarus is our team name that Scott came up with. I think we have the best name, but I don't know. That's just me. I'm biased. So it stands for Icarus is a robotic unmanned scout by me, Scott Jeremy. And this is the only slide that I really want to present, and I think that everybody has put the origin of their names. So so Icarus is this Greek mythology character from Crete. So there's a little bit of a tie with it's a team there. So the story is that him and his father, who is like the old man in this picture, Daedalus, they built this labyrinth in Crete to put Minotaur in there for King Minos. But then they were put into that jail of the labyrinth maze jail because Minos got mad that Theseus was able to like defeat Minotaur and like, you know, I don't know, become a hero. So they were put in jail, but then Daedalus, who is like this, really smart scientist and engineer that we were trying to be during this week, thought of a plan to like glue together some feathers with wax so they can like fly away. And unfortunately, Icarus, like his son got too arrogant, flew too close to the sun, and then the wax started melting and he fell down to the sea and died.
But he auto landed.
Out of it. Okay. So between the two men here, unfortunately, our drone was more like the Icarus, so it would just like randomly die time to time. So it was a little bit hard. That was one of the technical problems. Like we would turn on the drone, connect it, but then it would just decide on its own, like, okay, it's done. Even though the battery's not dead, like it will just shut itself down. So I guess the name is somewhat fitting in that sense. So the project goal for us is, well, despite the kind of, finicky drone, the goal was to put Monty inside there. So there are some unique challenges for the drone team, like kind of the starting point for the drone team is the camera that is attached to the drone. So we are implementing a distant agent. So in Monty, that means like, the agent or the drone itself is, basically not on the surface of the object. With this, so we get this, like RGB, normal picture from which we had to kind of do novel things like depth estimation. Well, I guess everybody had to do it in some sense, but depth estimation, object segmentation, and projecting that to 3D space. The ideal goal was to learn all the real world YCB objects that I think mostly Nils ordered from Amazon. So this was like the spam can that you see here. There are some hot sauces, Numenta Cub, mustard bottle, etc., and to perform inference on it. So our general plan, or it says current status, but like our general plan on how we approach this problem was kind of split it up into like two different kind of areas. So one is kind of the input area, which is a data loader, and the other is the output area, which is the motor system. So in the data loader section, the plan, was the general step is to take a picture with a drone. That picture is like a really large. I guess it has the whole view of the object. So for Monty, we need to take little patches of it. So that's what patchify means. For each of those patches, we need to be able to estimate the depth, get the semantic label. So that means like, okay, in the picture, if wherever in the pixel there's an object, we put a 1, and then wherever it's background, we'll put a 0. That's what semantic label here means. And then using the above depth information and the semantic label to be able to project to 3D coordinates. There were other challenges that we had to kind of do called side quests to actually like implement this. So like one was keeping drone alive. Like I don't know what's a better name than this. It tells you what it is. Keep drone alive. We worked something calibrating depth. We worked on some semantic segmentation, something called very good detection. So I'm not going to go into each of the in detail because it can get quickly technical. Do you want to comment on the motor system, Scott? Yeah.
Sure. I guess I'll just say that knowing the location of the drone and knowing the depth of the stuff it's looking at are obviously very crucial pieces of information for Monty. And so these were real challenges that we kept kind of trying to pare back. Like the rotating span here is at one point we just kind of realized we weren't going to be able to control the drone in real time and do what we wanted. And so this is just one of our like sort of simulated setups that you're looking at. So as you know, fairly early on, we sort of abandoned real-time drone control.
Yeah, and we'll show you the real-time drone control in our demo because I think that's the only thing we can show. And you guys can see like how the drone motor system kind of works. But here, anyways, like that, this animation is basically simulating, okay, like if the drone is flying in a circle around the object, like what is the kind of image that it would potentially take? So
Right. So that image is just because we like produced this ground truth data set, and I just wanted to make sure that the coordinate systems were as expected based on the geometry and making sure everything was aligned. But that's all that is.
anyway, I have a request for Will is to make this GIF into like a official TP thing. So, and then I'm going to speed it up so that like whenever I'm thinking, instead of my brain wheels turning, I'm going to say my spam wheel is turning. Okay, so keep that in mind. I don't know if we can make this like a Slack sticker or look like what is it? One of those like emojis.
Emoji.
Yeah.
I'll remake it if we want to go official.
Okay. All right. Yeah. But anyways, that I want my spam wheels to be turning for brainstorming. That's my thing. Okay. Depth estimation. So I think we have pretty similar challenges as like the Monty Meets World from last year or 2 years ago. I don't know when it happened, sorry. But in this case, I think they had like a true depth camera from iPad or some like other way to estimate depth. In our drone, like it's not a fancy drone like the Microsoft Connect where it can actually get the drone data by LiDAR. It's just RGB image, so we have to do our own depth estimation. Thankfully, we were able to use like a deep learning model called Depth Anything V2 from NVIDIA to get a depth map. And here's some example like outputs, RGB image and the depth map. So the lower value means that it's closer. So in this like image, the camera is pointing slightly downward. That's another thing that we noticed. If the drone is flat, the camera is a little bit tilted downwards, which is kind of weird. But that's like fixed into the drone, so there's nothing much we can do about it. And then anything like in the yellow is kind of like far in the background. We did that also for this kind of makeshift box that we made to calibrate depth. So here, like the depth value that you get is kind of like random value. So the lower is closer, higher is farther, but it doesn't really mean anything in meters or anything like that. So so we did a calibration where we put a box in like a known distance, and then we can kind of pick a point on like how far away that is. So
yeah, so that box is slanted away from you, so there's a bunch of known points there. So we just fit known locations against the estimated locations so that we could try to
it kind of
remap it into actual like meters basically, because it comes out but it turns out that it worked really well in this particular example of a single box. But when we try to apply it to we took that fit and applied it to like a spam can, everything came back kind of weird. So there isn't really one set of parameters that is going to like invert that. So I have a feeling that the depth map might be kind of sending back like relative differences between things in the scene, and it's not really something that you can just undo like to try to get units. But
anyways, there's multiple challenges, but many things. And then another thing was segmentation. So this too I graciously taken from the Monty Meets World. I'm trying to see like how they did their like depth like object segmentation. So in our current Monty, we have this kind of idealized simulated world where the object just floats in space with nothing around it. Like it's literally the object floats in, with nothing. Yeah, so it's very like non-real world. There's like gravity is turned off. We can see from the bottom of the object. In real life, we can't do that because it's sitting on a table, right, or on the floor. So and because the depth map that we're getting has like very it's not kind of like one flat depth map. If I try to threshold it, then some parts will be like the floor would sometimes be included. while not all of the cups is included and whatnot. So again, and we just implemented an alternative way to segment the object using, again, another deep learning model called Segment Anything Model, SAM. And then we use this kind of information to kind of cleanly take out the, it's not perfect because it's missing some of the muck, but cleanly, as cleanly as possible, take out the object from the scene. So this way, if we segment out the object, then we can kind of remove all the background, we can remove the table and kind of put it into this ideal world in our Monty world where like there's just a clean object floating in space.
Do you have to choose which object to segment out of the, like, do you have to, like, say?
Yeah, so I mean, because our object, I mean, I assumed that the object was at the center of the picture has the object. And then in other cases, I drew bounding boxes.
Okay.
You might have seen that on the Slack. This one I'll kind of go over quickly, but there's basically some tricks in computer vision to again, like extract out the real world coordinates with respect to some kind of a landmark. So there's this like QR code like landmark. We can say that the middle is like 000, which means that then we can 000 is in x equals 0, y equals 0, z equals 0. And using that information, we can theoretically get like the actual position of the camera, actual positions of the ground truth object, and same for pose and rotate, the pose or rotation.
Yeah, the main thing here was when we were flying the drone didn't know where it was in space. So the idea was to look at this code. If we knew the position of the cube and the orientation of the cube, and then the drone could know its position and orientation relative to that QR code, basically.
Yeah. And if you look at the values, they're actually quite sensible. So it says, so this is all in meters. So this is like just 0.8 centimeters. So yeah, you can see that it's pretty like looking at the marker dead on. So the X and Y values are pretty close to 0, while the Z is 20 centimeters or 19.1 centimeters behind. And that's about the location that we put the drone in. So it's pretty good and accurate, like estimation of the position and also the rotation. So you can see that there's a little bit of like tilting, like with roll pitch, and then the yaw is kind of flipped over -80. But I think if we need like real world things, then this is a pretty good way. I think Will came up with this idea, so thank you, Will. I didn't know about this until this hackathon. So anyways, with all the depth information and the segmentation, so we are able to put it into kind of 3D points. So all these images are kind of I mean, they look like just pictures, but that they're actually very densely sampled points. So individual there's like 100,000s of points here that make up this object. You can most clearly see it in this picture where you can see some stray like points coming out. So because we took the span picture in like multiple different in 12 different locations around the circle of the object, we tried to project each of the images into like a 3D point. So this is kind of the result of our depth to 3D and everything. So individual pictures, they turn out okay. You can see that it's quite like sensitive to like specific parameters. It can look quite distorted even if the picture is okay. So this was like one of the more, I guess, tricky parts. And then I think trying to put all these 3D coordinates into the same space was the most tricky. Actually, Scott, do you want to explain like this?
Sure, yeah. So like on the left there is with the so once we calibrated the depth, we had a mapping from the values that Depth Anything gave us to real world based on the calibration. What on the left is what the point clouds look like after calibration. It essentially kept thinking everything was super close in the center of the screen. And so, so after that, I thought, well, maybe if we just like adjust the distribution for each point cloud to move it towards, so its center is near 20 centimeters, which is what we knew we were actually from. So we'll just push everything back and see if that helps. I mean, there were just like so many things that we just threw at the wall to try to see if we could get these things into a reasonable 3D space. I think the one on the right
Yeah.
is from the non-calibrated just
Yeah.
raw depth. So
No, it's from real depth, but from the less precise estimation.
which turned out to be better. I
Yeah,
mean,
so, anyways, and you can see that like you can see individual spam kind of pictures that you would have taken. Like this would have taken this image here would have been like looking straight at it. This is at a slight angle. This is at a slight angle. But we're somehow putting it in a way so that we're modeling inside out. Like you can see that like ideally you'll form a circle, right? Instead of this kind of octagon, dodecagon shape. But this is as far as we get in like a week.
yeah.
Yeah. I mean, there's many lessons learned. We just didn't put them all here.
I guess I think there's just a lot to break off on the like getting going side on the drone project. I think probably just like starting with something that's already got some better ability to control the drone, know where it's located in space, have good reliable sensor data is probably a better starting point for just in a week. Like we were so close to being able to get Monty to push data through Monty, but to be honest, and we wrote the data loader and everything, it's like ready to go.
Yeah.
It was just this step of like, we've got this data that we can't figure out how to get into the same space reasonably as what's in a pre-trained model. Like at a minimum, the units in the scale are going to be completely different. But
definitely like I'm not saying that, but I think this is a very doable and like not maybe there's just not in a week. But like Monty can definitely live in a drone. I mean, if you get a little bit better drone, then we can actually get some like real-time feedback. And that'll be also kind of good because one of the other issue was that we had to connect to the drone, we have to give up on the house Wi-Fi, and just we take a picture, but then we realize, oh, the drone is actually tilted, or it's too far away, it's too close, or it's so like we have to do a lot of like physical manipulation to take good pictures like that. So I know that stop animation here is like. It's cool because like Scott and I like measure the exact distances and the angles to get this to get it as precise as possible. But thankfully we have some wet lab experience, so this was okay. So this was like overall like very like informative. I mean I definitely learned a lot about depth of 3D. I didn't get to play around with the motor side still, but at least on the data loader and a little bit of the sensor module, I think this was very informative.
Well, very cool, very fun project. I just like wish that we would have been able to jumpstart getting the data into 3D space a little quicker so that we could start,
Yeah, and Jeremy actually worked on a lot more of the motor side to keep the drone alive and move in circles. It's just that it never, we don't have any outputs for those because like we never got like the data to Monty and to like emit a motor signal like move up and down, like, but if it were to say like move up, then like Jeremy's class would will be able to control the drone that way. So if we don't have to return the drones, maybe like Scott and I will take one each back and work on it a little bit because I think we're super close. So
I think I start with a different group.
Yeah, it's really cool. And yeah, it kind of like you guys are saying, it sounds like there's a lot of pieces that are just like super close. And maybe if the hackathon had just been like a few days longer, because I think you guys definitely had a challenging one with all the different pieces and stuff.
Yeah, and I think that was kind of also at least what we imagined that people spent most of the time on during the hackathon will be like the robotics side, like assembling the robot, tracking the locations and everything is definitely like the hardest part.
And it's the kind of stuff that it's good we're not trying to do like normally kind of 365 days a year, but it's useful to dip into it, I think, for a little bit and just kind of appreciate the challenges, appreciate yeah, what assumptions we're relying on when we are working with simulations and things like that.
Yeah.
For sure.
Yeah, cool. Thank you.
Yeah.
Were those all your slides?
Yeah. So yield the floor to the next team.
Well, wait a minute. I have a couple of questions. Could you explain
yes.
to me the your explanation of how this demonstrates Monty's capabilities, and also how does this show for Monty's future, in your words?
Okay. So in terms of people, do you want to? I guess.
Well, look, a bird.
Yeah.
Oh my God. It's hard to say, like, we got a lot of experience with Monty in like prepping to lead it up to it. So like, I learned a lot about how we might be able to sort of make the process easier for like jumpstarting a new project. But we, of all the teams, we're not going to be the ones that give you a really good answer on like the future of Monty, because we just didn't really get that far along to where Monty was really a big part of the equation.
So I mean, yeah, within a week, in a week. But I think in terms of like real world application, probably among the three of us, drone is probably the most accessible for the public. So that means that if we can put Monty into the drone, we just haven't gotten there in a week. But that means that if somebody had like a flying agent of some sort, then we can readily apply Monty so that it can do object detection and pose estimation in the wild. So I guess that's about the Monty's like futures. I think demonstrating Monty capabilities. I think this we haven't extended any capabilities. We're just using the existing like learning modules and
So I do think we could have, in terms of like the future of Monty, we could all get together afterwards and talk about what kinds of like architecture we might be able to add to make something like pre-processing things more plug-inable, on that end.
We got a lot of user experience and like what if somebody wants to adopt Monty into their project, like what kind of challenges they might face. So to make that easier for other people as well. So I think we at least gain a lot of insights on that. So.
For sure.
All right. Sorry, that's all we have probably.
But what with the technology that is already exists, how would Monty improve that? I mean, it seems to me like there's drones out there that can pretty much, are they specifically just done on location, or can they actually, are the drones now, can they recognize what they're hitting? I mean, is there any kind of visual recognition, or is it all based on location?
I mean, so once we have the images, then yes, Monty will be able to recognize like different objects that exist in the scene. So right now, like it's just a spam can, but theoretically, a drone can fly around and kind of put like boxes around. Oh, like I see spam can, I see mustard bottle, yada yada yada. I guess in that sense, like it's kind of similar to like some drones, like if you do like just pure deep learning way, like I've seen like some demos where it's like trying to do object tracking, for example. It is at that level, but we're doing it in the I guess the sensory motor way instead of the deep learning way.
Yeah, I think that the main point that it would show is that Monty is a sensory motor system. So that was one of the ideas that for this drone project, that the drone can intelligently move around the object. It's not just like a static image that it does image recognition on, but it like uses its learned models to move in the world in an intelligent way. And so if it tries to find a specific object or tries to recognize an object, move specifically to where it needs to collect the information that it needs to determine object ID and pose. And yeah, it's not like a static image recognition system.
So right now, do we only have, I mean, that you know of, is that the only things the drones can do is static recognition and not anything else?
It's kind of like I think in general it's a mixture. Either yeah, it would be more kind of static, or kind of using single images that are coming in, or there's some drones that might be specifically designed to build a particular 3D model, like let's say a 3D model of a building that is being surveyed or something like that. But so, you know, right now you wouldn't go out and use Monty instead of that. But the whole kind of idea of how Monty builds representations that become more complex and more abstract means that, you know, with a full Monty system, it would be able to understand the environment in a much more intelligent way that no drone can right now, because there just isn't an AI system that can understand the environment like a human does.
And it can like continuously learn on the fly. Like it can go into like a disaster zone and see objects in configurations it has never seen it before in the training distribution, and learn those really quickly, and then recognize them or feedback to the user what it's seeing, or like where trees are blocking a road or something like that.
Okay.
I think we may have taken up too much time, so move on, maybe? That's okay.
Yeah.
All right. I will stop sharing. And okay.
I'll plug Hoja for creative solutions, because like that Aruko idea was really nice, really elegant. The idea of figuring out where the drone is positioned in space based on things like QR codes, really nice.
I'll toss that compliment to Will because it was his idea first. So
Okay.
it's
Actually, yeah, I
Altruist
want to quickly ask
comments.
about that. So could you calibrate the depth with that? Because if you knew that was 20 centimeters away and it was in the depth image, could you just say any pixel that's at that point? Or is the issue?
Yes.
Okay. Okay.
Yes, yeah, that would be the most ideal. But I mean, we did the slanted book thing so that we can get different depth.
Okay. Yeah. Do you do multiple of those codes or?
Yes. So I mean, I printed out 4 and put it on 4 sides of a cube. But it's
Or like
basically
even in different planes?
yeah, that's fine too. Like technically I can put it in like all 6 sides, and each of those, actually the more is better because that each of them will give you some kind of estimate, and then you can take the average of those estimates to get a more precise pose. One of the reasons why I like we're not getting like perfect numbers is because, you know, I'm just estimating from one marker seed. Actually, you can, you know, detect multiple markers like that. Actually, that would be more ideal. And then kind of aggregate information from there.
Yeah, maybe we have a follow-up meeting
Yeah.
sometime to go into
Yeah.
the details and just
Yeah.
do like the high level
Yeah.
presentations for now. Otherwise,
For
we'll
sure.
take a long time with the demos. Okay, yeah, Lego team, do you want to go next?
All right,
And yeah,
Uh,
try to keep it under 10 minutes if you can.
let me share my screen. 1 second.
Do you have music in this presentation?
No, we should have added the.
Now you should add the background track.
Okay, everybody see this? All right. So hi, we're team Everything is Awesome, Rami and myself. There we go.
Explain the team's origin, please. Just kidding.
So in the beginning, we got some Legos, bought a bunch of stuff, started assembling it into a platform. And then this is the platform actually running. So this is our robot assembly. So that's one of our motors and part of our motor system. Then we were calibrating it very scientifically of seeing how fast the thing can go. And so we calibrated it well. Then we also, so the other part of the robot is a sensor module. This is the elevator that goes up and down. And in the background there, you can see this is the sensor with the camera and the depth, with the RGB camera on it and the depth camera on it. So, and that's what the robot looks like combined. We did a bunch of debugging. This is an example of debugging the depth sensor. There's interest, like you can see different depth resolution versus RGB resolution. So every dark point is an RGB point, and the depth sensors were like more pixelated squares. Some of the lessons learned. Early on, we're trying to remind each other not to eat the data set. Since some of it was edible and it was in the kitchen, so we just finally separated out of the rest of the food that we planned on eating. Another lesson learned was it was really great. I think everybody was mentioning this, building something with Monty end to end, so that we had to write and understand every single part of the Monty system. Like I know Rami and I are way more familiar with how the whole system works now. Of course, quaternions. I understood quaternions for a little bit, so that was great, and I think I still remember them. There's a resource that really helped with the intuition. Some of the Monty framework things. There's some ideas for action refactors that I want to do after we're done. Noticing too many resets happening before an episode. Like, if you're running a simulation, you never notice it. But if you have a robot, it's like, why is it doing the resets so many times before it starts? So that was a neat finding.
Yeah, we ran into the same problem, spent way too much time on it, and then decided that we'll just always have to press the button twice before we start the experiment.
We had to do the same. Like we had to take 2 pictures, and because the first picture would always be black for whatever reason.
Nice.
Yeah.
I removed the extra reset, so that was my. Because our coding approach was we just forked the entire Monty repository and we just hacked whatever we needed to. So that was convenient. That was also a convenient approach to the hackathon for us.
Yeah.
Picking coordinates that make the problem easy. As you saw, our robot has a central platform that rotates and a thing that goes up and down. So we're like, our units are the robot radius and we are on the unit circle, and that simplified a lot of things immediately. So that was super helpful. Next on debugging and visualizations.
Yeah, I think to me, I feel like having a very good, this is what I figured out early on, that if you have very good visualizations and a debugging, that will go a long way in something like this. So yeah, we started working on some nice visualizations. You'll see that in the next few slides, but basically we're able to see the sensors positions live as it's basically making movements, and basically also what the current MLH is, or what Monty thinks is happening and what the rotations are and all of that stuff. We had some trouble with the coordinate systems, so we started using, so for the get state of the agent, so that we know where the agent is, we're using a different coordinate system that was in Monty, and we figured it will still work fine. But then it does not plug well with the depth to 3D, so we ended up changing all of our computations for the get state of the agent, and that's where learning the quaternions also, that's where we started looking into quaternions too. And then we tried to do model scaling, so basically we're using different different scale than what is in the data set that was provided to us before. So that did not work very well, and I'm not really sure why, but so we added some code into the grid object model that will basically, you can just say scale this model by this scale factor, and it will just scale the mesh and recalculate the KD tree and everything. But that still did not help very well. So what we ended up doing is that we basically trained our models, but then the models that we trained are very sparse, so they may not work very well. But the idea is that if we train a dense model, it will work better. But you'll see that we still have some performance, kind of reasonable performance. And early on, we, in the first day, we had a lot of networking issues, and it basically, the reason is they have multiple sources of, they have multiple routers, and if you have the different clients are connected to different routers, they'll not be able to talk to each other. So what we ended up doing is that we needed a router, but then we could not make that router connect to the internet except through like a hacky solution where we plug it into a Wi-Fi extender, and that Wi-Fi extender gives the internet to the router, and then we can connect to the router. So, but the cool thing about what we built is that we could actually like decouple the simulator from Monty itself. So what we tried is running 2 different Montys on the same hardware. So basically, Tristan and I, we were running experiments at the same time, and we were fighting for the hardware, which was very cool to see basically like the sensors moving. Like I give it a command to move somewhere, and then Tristan just moves it somewhere else, and then we start arguing about, you know, needing the resources and all of that. Yeah, and a lot more stuff that we, you know, the depth camera was like giving us a lot of trouble. So yeah, too much troubleshooting and debugging that went there. And yeah, like I said, a debugging setup goes a long way. Yeah.
Okay. So we did some, so with troubles with changing the scale of the existing data set, we ended up training on the data set ourselves. So if you don't recognize it, but that is a cup. All right, and
Yeah.
so this is training sped up 40 times. So on the left, you see the visualization being built, and on the right, you see the robot using our training policy was essentially orbit around the object from the bottom up and just kind of scan it. And so that's the idea behind that. This is what the final scan for like the cup looked like. So it does end up looking kind of like a cup.
It looks like a cup, but the handle is,
Yeah.
I think we have some trouble with the depth information and maybe the focal point of the, like the field of view and all of that stuff. So it's a perfect circle and everything, but like the handle is a little detached from the cup. And this is why our evaluation works fine with the trained models, but then maybe this is why scaling the meshes didn't work very well, because they're kind of different. During inference, we can see that you know, so this is a different kind of visualization where it's basically I'm plotting the current MLH in real time. So it's basically if you can figure out the rotation, the rotation. This little dot is a sensor. Basically, this is where it thinks the sensor is compared to where the mug is. And it was able to figure out that the cup was right side up, but it could not figure out the rotation, like basically the rotation on the y-axis, or like where the handle is. So, but it could separate it from all the other objects in the data set. So that's also good.
Yeah. And essentially we used based policy, just random actions. We had to kind of rewrite it a little bit to use our actions, but as you can see in the video, those actions are just purely random, the up, down, and rotating around the object.
But the sensor's always guaranteed to be on the object in these
No.
cases.
No,
How do you move back?
it's random.
It's built in. It's
Yeah,
just-
yeah. So if you're
How
off
do you-
object,
how does it know that it's off object? I guess is my question.
Well, there's the transform, right? So based on the depth, it knows that
I see.
the depth is.
yeah. So if the
Okay.
depth is like too far, then you're not an object. So
Okay.
we go through the
you have
building the semantic labels based on the depth.
Okay. I have more questions
Okay.
we can get into.
Is this the time for live demo, or do they come after all the presentations?
Maybe we wait until after the presentations and we pick one object that we all demo on.
Okay, sounds good. That's it.
Nice, great job. Looks really cool.
So can I ask those same 2 questions with regards to,
Yeah. Could you ask them again?
yeah, I gotta bring them up. Okay, how did your project demonstrate Monty's capabilities, and how do you see Monty with the application you're doing for the future?
Yeah, so demonstrating Monty's capabilities, I think this would count as probably, I don't know, but I'm not sure, but this is probably the first system that has actual movements in the world, basically, instead of like saccading over an image. So it's not like we're taking an image and then we're moving a patch over the image. It's actually the patch itself is moving through the world, which is, in my opinion, is very different from what we had before. So it's demonstrating a different side of Monty's capabilities with an actual motor, basically, so that this thing works as a sensory motor.
Okay. Yeah, can I throw in there? So like just one point about the patch, like in the previous presentations, you saw like a full image of every, like being taken. Literally, Monty only sees those dots. Like there's nothing else. There's no image of the cup. There's nothing. Monty learns just those dots on the left. And based on that, it learns to recognize objects. There's no full picture given to Monty at any point.
Good.
Yeah. And then in terms of future capabilities, I think that so this is a first step. In my opinion, there's just like with the drone team as well, there would be opportunities there to explore boating, which I think is very important. It's easy now. We're building this with Lego, so it's easy. Like we could add a different sensor and that's a different angle, and then we can just move it. We can move it independently, or we can move them together as part of one agent, so they can move like like two sensor patches on a finger together, or they can move as like different hands, and then they like look at different parts of the mug. And so basically, it's very extendable the way that we set it up. So yeah, if that answers your question, I'm not sure.
Yeah, I think it's a great point. Like, it's the very first time that Monty is working with a motor in the real world. It's a huge thing. And then I guess just for us, it will be a great setup to have to test Monty in the real world. Right now, we basically everything that's a bit more complex, anything that involves movement, we have to test in simulation. So now we have a test bed in the real world, and we could give it any kind of object. We don't have to create like a simulated object data set or anything. We can pick something from the kitchen and put it on the platform, see what Monty does.
Yeah, yeah. It also scans very nicely. It scans very fast, but then it's still kind of sparse compared to what I would expect. Like I looked at the meshes that you gave us, and they're very nice, but like very dense. So this is like sparse, but the fact that it still works even with those sparse models is mind-blowing to me. So
Does it work? Does it work at any speed? I mean, if you slow down the motor or speed it up, does it still have the same results?
Well, slowing it down is always easier. Speeding it up, we're running at a kind of a high speed actually, and but we're limited by how much time it takes to transfer the image from like wirelessly from the sensors to the computer and process them. This is actually the bottleneck. One of the challenges was I was sending a bigger, so that to be able to stitch the depth camera with the RGB, I was sending both like bigger images from the Raspberry Pis or from Monty, from the robot to the computer, and then stitching those. But then we found out that if we just send the patches and do the computations for which patch we want, which just basically sends smaller images across the network, it goes much faster. So Monty doesn't have a problem. Actually, Monty is much faster than the bottleneck of sending images. So yeah, it works. It works fine with high speeds, I guess, short answer.
And yeah, to Monty, it doesn't matter how fast you move or in what pattern you move over the object. It's not like you need to have seen that pattern before during training. You can generalize to any like speed of movement as long as, like what Rami says, the transfer is fast enough.
Yeah, and you can increase.
You're muted.
You're muted.
And you can speed up the inference by having Monty have multiple sensors. So I have like 1,000 sensors looking at something. You can recognize it instantaneously rather than having to move, or you can move it once. So yeah, you can. Once we put this in hardware, this could go very, very fast.
And another thing about the future, demonstrating future capabilities, as we have zero precise movement. So when the elevator goes up, we ask it to go a certain distance, but it goes whatever distance it manages. Like there's minimal distance. When it rotates, we're like, rotate by 7 degrees. It's gonna do whatever it wants. So, but as a result, we were able to work on proprioception and make sure that Monty was still processing where the thing actually was. So there's no, so what we also demonstrating is you don't need any sort of precise movement as long as you figure out where you end up. And the policies still seem to work okay and still infer and train objects, even with imprecise motor control, which
Yeah,
is
that's cool.
a new demonstration outside of simulation.
Yeah, actually, there were some times where the rotation robot, that one that rotates the platform, it was not even moving. Like it tries to move, but it looks like it doesn't have enough power, or like we're just doing small steps. But basically, because we're using proprietary, we're getting the position of the agent. It doesn't matter. So basically, we'll just add points at that same location, or depending on how the object is built, it doesn't need to add these points. So the lesson learned is that just being able to get an accurate position of the agent is more important than moving the agent, moving the agent somewhere, or trying to move it to somewhere accurately. It doesn't matter as long as you're able to get the position accurately. So that was helpful.
Yeah, awesome. Looks great.
That's how they got their name.
Yeah, everything's awesome.
That was Tristan's idea.
All right.
So
Cool. Then yeah, I guess it's our turn. All right. How do I start the presentation? Sure, right. Well, I think this.
Yeah, I came up with the team name. So this is where the team name came from. The movie Kindergarten Cop.
What's the matter?
I have a headache.
It might be a tumor.
It's not a tumor. Not a tumor at all.
At all. And so we are the ultrasound team. I'm Will, and Vivian, who you know, and Niels. And so we are scanning things inside a bag that are not medically related. So that's why we call this not a tumor. Let's play it again. Let's keep out of this. Bum, bum, bum. Okay. So this is the ultrasound that we've been using. We got this on loan from Butterfly Ultrasound. So this is it in my hand for scale. And on the right is an actual ultrasound. At the top, you can see the bit of the probe. And then down here, you can see something that's definitely not a tumor. This is the cross-section of a French's mustard bottle. So that's your primer for what ultrasounds look like. Good luck.
If you weren't able to tell, I mean,
Yeah,
it's pretty obvious.
It's pretty obvious, really. Come on.
Yeah, and what's exciting about ultrasound is obviously it has a huge number of applications, medical being one of the main ones, and it's an inherently a very sensory motor way of clinicians understanding what they are seeing. And it's very challenging to use AI for this because in the medical field, you generally don't have large data sets. There's lots of reasons that Monty would be perfect for this kind of use case. But ultrasound is not a very intuitive modality, at least if you're first dealing with it. So, this is, for example, what the 1000 Brains Project mug looks like in ultrasound, or part of it, rather. And what you need to bear in mind is that ultrasound, the probe is producing a two-dimensional beam, like a fan. But that two-dimensional fan is moving in three-dimensional space, kind of going through a structure. And as the name implies, the probe is emitting sound waves, ultrasonic sound waves. And basically the time it takes for that to bounce back tells you how far away something is. And the intensity tells you kind of how white that is. So something like bone or metal or ceramic, like we were dealing with, tends to show up as really intense, really white, whereas kind of soft tissue and things like that appears more gray. And then water would just generally appear like black. And so that can give you a huge amount of information, but it is challenging to work with. So, for example, the TBP mug, as I was saying, this is an image of it. And in particular, it's an image, a 2D plane kind of going through the side of the mug and side of the handle. And so what you're seeing here, for example, this is the top of the cross section of the handle. If you can imagine you had like a very sharp saw that went straight through here, this would be what the top of that would look like, and this would be the top of the side of the mug. But you don't necessarily see everything you would expect because, for example, you get what are called acoustic shadows, where the sound cannot continue to propagate, and so it's black behind this edge. And you also get lots of artifacts. So these can be caused by various reasons, but if the sound wave gets delayed, if it gets reflected multiple times, all this kind of stuff, you can basically the image kind of hallucinates. As far as the probe is concerned, it thinks there's objects out there in the world. And so these were kind of some of the things we had to deal with when interpreting these images.
Yeah, so it also turned out to be quite a lot of moving parts to setting this up. So I'm just going to talk you through the architecture diagram really quickly. So over on the left, we have the ultrasound device. To it, we strapped an HTC Vive location controller with just a piece of Velcro. When you click the button on the probe, it captures what the probe is currently looking at and sends it to Monty with some metadata about the depth, the scale that we were looking at on the image. At the same time, the HTC Vive controller is streaming its location to two sensors on the floor, which then send them to, not pictured here because it was even more complicated, which is then streamed to the HTC Vive service, where it stores the current orientation and three-dimensional location of the probe. As Monty processes, it gets that image and then it asks the Vive service for the data, and then it visualizes that over here so we can see what we're actually looking at. It will also suggest where you should move to next. So Monty can't move us, but it could tell us where the next best view to get the next best inference would be from. And then also a visualization of how Monty is doing what it's learning as we go. And so you'll see all of this in the demo. We want to just give you a quick overview.
Yeah, and so one thing, just to kind of give you a bit of a sense of what the whole thing looks like. So we had what was called a phantom. So a phantom is when you're kind of testing ultrasound or someone's learning how to use ultrasound. And so you have kind of an artificial structure that can be scanned. So, might have an obstetric phantom. But since we were dealing with objects that Monty has learned in kind of simulation, like the YCB objects, we created this setup with essentially a plastic bag filled with water. So, you can imagine it's something like an amniotic sac with objects suspended inside of it. And then all of this kind of set up with some tripods so that we can kind of move around it. And then, we're basically putting the probe on the surface of this bag with some ultrasound gel so that it kind of gets a consistent propagation of the signal. And of course, the task is to determine what object is inside the bag. And as Will mentioned, we were kind of tracking the position of the probe. The way we did this was with these what are called kind of base stations. These are actually designed for virtual reality gaming. And so people have already spent a lot of time engineering a good solution to this. And basically this tracker, it actually is this tracker looks fairly kind of, static, like it's not doing much, but it's actually looking for kind of invisible lasers that are coming out of these two base stations on either side of it. And that tells where it is, and as well as its orientation in the world, and quite a good amount of sensitivity. So that was really useful for this task.
And so after we basically get the ultrasound images plus the tracking data of where the probe is in the world, we now need to extract some more information from the image. And so this is the processing pipeline. First, we have the environment class from Monty that we customized so that it gets both of these types of information and synchronizes them. Then in the data loader, it actually we look at the full image and try to find a small patch in there, which should be on the surface of the object. So how we do that is we basically start in the middle and move downwards until we detect a significant edge. And then we extract a patch around that. And then from that patch, we detect some point normal and curvature. And we combine that information plus this distance from the top to the patch, plus the tracker pose to get a CMP message to send to the learning module.
So in the demo, you're going to see this iPad app, just to orient you to it. So we have the image here, and then we have kind of the depth that we're shooting at, and the gain is kind of how white this image is. And then we have like the number of images we've captured so far. It starts at -2 because obviously the first 2 don't count, as we all found out. And then like a manual capture button here. We are set to the default type of musculoskeletal, which we found was like the best for identifying the kind of hard objects that we have in the demo. So that's going to the iPad app, just so you've seen it.
Yeah, so a bit more detail on extracting the patch. So there were several difficulties. So like the acoustic shadows and artifacts were really giving us some trouble. So for example, sometimes the highest peak in the kind of edge detection is not actually the object. So in this case, we actually want the patch here, not here, because this is an artifact. And so we had to do quite a bit of fiddling to figure out the right settings and right kind of algorithm to get the patch off the surface. And then next, we basically figure out a bunch of points on that surface and try to fit a circle through those points. And that circle tells us about the curvature at that point. And then we also try to estimate a point normal at that center location, which can tell us about the pose of the patch. And that also took a bit of fiddling because, again, there are all these little artifacts that sometimes get these blue dots to show up in the wrong locations. We had to kind of sometimes limit the range in which we try to fit the circle because like surfaces like on the brain are very bent. But yeah, eventually I think now it works reasonably well. And then we have to combine the depth, the sensor, and the agent location. So if we just look at the agent location, so just what the HTC Vive returns, we basically get the shape of the bag. And then after we add the depth that we extracted from the patch and the kind of offset between the probe and the tracker, we get more something that's shaped like a mug. If you have seen it many times, you see the mug, but if this is the first time you see this, you might not recognize it.
It's not a tumor.
Yeah. And then we added
Yeah,
some,
but it could be a lot of other things besides a mug.
but yeah, so if you visualize it as 3D, so you can kind of rotate it. You can't see it on the slide, but if you rotate it, you see that this is the body of the mug, and then down here is the handle. It's a bit hard to get a good screenshot of it. But yeah, it does look like a mug. And then we added a bit more live visualization that we can run during an experiment so you can see what's going on. So we have the input image and we have the extracted patch. You see how we fitted a circle through that patch and a point normal there that we extracted. And then that gets combined into locations and orientations in a common reference frame, so like relative to the world. And over time, while we move the probe, so each of these blue dots here is basically Niels moving the probe to a new location and taking another picture. So over time, you kind of have a bunch of points and they update our hypothesis space. And then eventually you have a most likely hypothesis and a couple of other possible objects. And eventually you hopefully recognize the object, which in this case we actually did. Even recognized some symmetry in the potted meat can. Yeah.
Yeah, and another thing that we wanted was to be able to show to the user, the person who's kind of operating this, where the probe is relative to this bag, that's kind of suspending the objects. And the reason we want to be able to show this is because, as you'll see in a moment, we also want to be able to direct the user where to move the probe. And, going into the farther future, if Monty was ever used, you can imagine someone who doesn't have a huge amount of training in sonography. If they can just figure out how to move the probe and they can get some direction about where the probe should move, then that could enable them to acquire some quite high quality images with guidance from Monty. But the first step in this is actually showing it, okay, where's the probe right now? And so that's what you're seeing kind of here, how we have this visualization of the kind of bag as this kind of cereal box like white rectangle, and then the probe as this blue rectangle. And you'll see this kind of live soon. But as the probe moves in space, the position of the probe in the visualization gets updated. But in addition to this, we can occasionally Monty reaches a state at which it thinks there might be a goal state that if it moved to, it could reduce uncertainty about what it's seeing. And this is what we call a goal state. And so that's what the visualization is showing here, is that at that point, this new blue arrow comes in, and that's basically telling the user, you should move the probe into this location. And basically that blue arrow will continue to be there until the user has moved the probe there. It's still up to the user to decide whether they acquire an image there or not. Monty doesn't force them to do that, but it's at least giving some kind of guidance about where an interesting view of the object might be to disambiguate what's being observed.
Yeah, issues encountered, as Niels already showed, it's quite hard to work with ultrasound data. When Will and I first got the first images, we were not very optimistic about this week going well for us. But with Niels's expertise, we got something working. Then second one, coordinate transforms are, well, as usual, a huge pain to figure out. Yeah, kind of like Tristan and Rami, you mentioned, like having good visualizations help, but still spend a good amount of frustration and time on that. And then the data streaming was a bit tedious in the Airbnb. The IP addresses would randomly change sometimes, and internet would drop out, and things would go to sleep, like the trackers kept falling asleep.
Or batteries dying.
Yeah.
Forgot to.
So just all the communication was a bit shaky between the 4 different components. We also tried to do a bit more AI-assisted coding, which sometimes helped to get hacky solutions, but also sometimes really did not help. Like it tried to import a module called Monty Python, and would just hallucinate some funny things. We could not resist that temptation to eat some of the data set. Tried to make a good case for why it doesn't matter if the hot sauce is filled or not. So it was open.
Doesn't affect the ultrasound image.
Yeah. We also had a magnitude 6.2 earthquake at 6 a.m. in the morning that woke us up, and for a couple of hours we were debating whether we should go into the mountains because there might be a tsunami. Luckily, there was not. And some family emergencies of kids falling downstairs.
Downstairs.
Oh my.
She's got a black eye now.
Yeah, and I guess there's a lot of kind of interesting things you could do in the future in terms of kind of shorter term things that we'd love to look into. A big thing is the challenge of getting kind of reliable features extracted from those images. And as kind of Vivian was alluding to, if it picks up on an artifact and it thinks that's the edge of the object, then in general, the representation's totally off. And there's a variety of ways we could kind of handle that better. One thing we don't have at all is, we're just kind of looking at the ultrasound as these kinds of images in 3D space, edges in 3D space. And that is important for how humans understand ultrasound images, but it's also only part of it. We also look a lot at what is the kind of actual texture of what you're seeing. So, whether it's a lung or gallbladder or whatever, all these things will look very different. And it's true of the objects we were scanning as well, but that's not accounted for. Curvature was something we didn't get to being fully integrated. We kind of measure it, but it wasn't in a way that we can compare it to the simulated, or the models learned in simulation. And then, yeah, we had kind of some ideas for how we could make sure we get this thing called the kind of maximum curvature dimension, which again was kind of working in principle, but just needs to be kind of made more robust. And then some of the things that we're actually working on the research side, like for example, Rami's working on with kind of resetting, re-anchoring hypotheses, would really help with the kind of robustness of the system. So one of the things we're kind of excited about is we've collected a lot of the images along with the positioning information and saved that, which would be kind of the start of a new data set where as Monty improves on the research side, we can actually rerun it on this kind of real world data set and see how it improves.
Yeah. It's a tuna.
Yeah, but yeah, there was a tuna can in the data set, so that was, I guess, one of the things we were practicing on.
This
But,
is Monty having, you can't see it on the screen, but its most likely hypothesis is the tuna can, which is what's in the bag. And here you can see on the iPad screen, you see the depth, the ultrasound image, and Niels is holding the probe against the bag. And then the data gets streamed to the Windows laptop and to the Mac, and Monty runs here. So that's the whole setup.
plus a bucket to collect water potentially leaking out of this, what's actually a urinary catheter bag.
So is Monty actually running on the Windows machine or on the Mac machine?
On the Mac.
Yeah, the Windows is only for so OpenVR, which is what is used to track the marker, the tracker. Doesn't really support Mac, or definitely doesn't support Mac, and doesn't really support Linux either. Especially like a headless Raspberry Pi without a GPU and all that stuff.
All right.
Okay. So how about answering the 2 questions?
Could you please
yeah,
remind
so-
us again?
How it shows Monty's capabilities is that it's like a very kind of shape-based approach to recognizing objects. It's not just like low-level features that it picks up, which it couldn't do much with in this ultrasound data. It's really about moving a sensor in space and getting locations relative to each other in space, which Monty is uniquely made for. Then also this kind of goal state generator that Niels showed with the point that tells the user where to move the probe next is Monty's intelligent action policy, where it uses its internal models to tell you which view would help most recognize the object. So it's not just like a random policy or like a methodical scan as any current ultrasound AI solutions are, but it's like very methodical about acquiring the information it needs.
Yeah, and then in terms of the kind of the long-term future applications, so of course it's not ready to be used now, but you know, with improvements and with improvements to Monty, this could be a huge help for kind of bringing ultrasound to parts of the world where any kind of medical imaging is hard to do. Ultrasound's amazing because you can hold it in your hand, you can connect it to a smart device, something you cannot do at all, of course, you know, with something like a CT scanner or an MRI. And it's generally safe. You know, there's no radiation and all these things. So it's an amazing technology in that sense. The real hurdle is that you need someone who had years of training to know how to use it and interpret it. And so there have been efforts to use kind of current deep learning systems to help with that, but they require huge amounts of data. They don't have this kind of inherently sensory motor or spatial understanding that enables them to suggest acquiring kind of data the way we've shown here. And so, yeah, this would basically be a way to bring the kind of benefits of ultrasound to many parts of the world that currently don't have it.
Yeah, I would echo that. Like the cost of the ultrasound was like $1,000 for an ultrasound. Cost of training a doctor is like $200,000 per year, and then hiring and that's a lot of money. And so the ultrasound devices are going to get cheaper, and it's very easy to get them out to places where they need them. And so I think highlight a point that Niels made about the lack of training data as well, is that medical data isn't very available, but especially abnormal medical data where there is a problem. Like if there's a tumor on the heart, like we don't have any scans of those because they're so rare, but you need a device or a system that will be able to say, hey, this looks like a heart apart from that bit there. So while we didn't get to that in our hackathon, like it was part of the stretch goals, and we think it would be enormously beneficial for being able to scan a healthy thing and then be able to tell the difference between an unhealthy thing without having any additional training data. It'd be really cool.
Okay.
Does that answer your questions?
Yeah, that answered my questions.
All right.
Demo time.
Yeah, then it's time for demos. Should we start and we go backwards in the order? Or
Sure.
Okay.
since we're already
I
unmuted.
guess maybe we can show
The Benny Hill music.
Yeah, so I'll show around the setup while Will and Niels get everything ready. So yeah, here's our Windows laptop that communicates with the Vive trackers. The Vive trackers are set up down here. There's one, I hope you can see, and then there's another one over there. And this is just strapping the tracker to the ultrasound device. So you can.
This is indicating it's on, and then this is connected to the iPad over here. It was a sufficiently complex setup that we ended up creating kind of like a surgical checklist that we would like go through every time to make sure that everything is running. Because yeah, we also have we have the Windows basically running the server, providing the location information. So yeah, so blah, 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 iPad.
While we're setting up, Terry, do you have an object that you would like us to test on?
What about this?
What are my choices?
So we have the TBP mug, we have the tuna can, we have a mustard bottle, the Spam can, we have a package of ramen noodles, we have hot sauce, we have a heart, and the little Numenta brain stress ball. Yeah, I think those are the objects.
Oh. Okay, so why don't we and these are all in your data sets? You already have these.
Yes,
these are the ones you
but
can use.
You would do us a big favor if you picked an object that doesn't float.
Oh, okay. Okay. Well, the heart probably floats.
Yes.
The brain probably floats.
Yes.
Does the mustard float?
A bit, yeah.
A little bit, but we can try it, right?
Well, let me ask you this, what doesn't float?
The Spam can, the mug, the tuna. Oh yeah, we also have some harissa sauce.
Oh,
And
let's go.
tomato soup can.
Let's go with the tomato soup can.
All right, we have never tested on that, so let's see.
It's
No.
I was just gonna say the tomato soup can is kind of, it doesn't have a distinguishing feature.
Oh, that's true. And it looks kind of like the cup. So let's go
Yeah,
with
exactly.
something.
The cup has the advantage that has the handle that kind of.
Okay, how does the hot sauce float?
No, the hot sauce might be a good one actually.
Let's do the hot sauce because it has a different shape. And how empty is the hot sauce, Niels?
No comment. Yeah, you may need to hold it, but I think that's a good one actually. Let me just fill up with water.
Yeah, Neil said that he wanted to be like a normal person for once and travel without hot sauce. And then he ended up eating our data set.
Not much control there, Niels.
But I was on holiday for like 2 weeks in America as well, so it was a long time without.
Well, America has hot sauce.
But not everywhere.
When he told us that it doesn't matter for ultrasound, it was a bit like an addict trying to convince us that.
Yes, yeah.
You still have the visualization.
So yeah, as things are shaping up here, you can.
So while you guys get set up,
Yeah,
it seems to me all three projects rely heavily on network.
Yeah, I think that's like a robotics inherent kind of problem.
Yeah, okay. Because that kind of eliminates you being able to go to different places in the world with your, if you don't have good network because of all the data coming in, right?
Yeah, if you would
Okay.
design like a full-fledged product solution, I'm sure you could also work with just cables to connect stuff.
Yeah.
So yeah,
Okay,
this is
yeah,
more like
funny
the
approach.
quick hacky version.
Okay, so we're gonna start inference.
Are you sharing your screen?
Yes, I am.
Okay, cool.
Okay, and then
So did you calibrate the track?
yeah,
Okay.
we've been through the checklist. So right now you'll be seeing you can see the probe. Sometimes it gets a bit laggy when we're on Zoom. Unfortunately, there's just too many devices running. But the kind of probe moving relative, and then maybe if you switch over, Will, to the other view, what we have here is a view of.
Try and make it full screen.
what do you call it? The
Yeah, on the top left, you see the full ultrasound image, and then next to it, you see the extracted patch and the features that we extracted. And then to the side of that, you saw the relative locations in the world that it estimated. And then on the bottom row, you can see Monty's current hypotheses of what it thinks it is sensing. So there's still, almost all of the objects are still possible, but the most likely hypothesis right now is Monty's heart. What did we actually put in?
change that? The hot sauce.
Hot sauce,
bottom.
okay.
So we have, in our kind of experiment setup, we have 30 steps to try and correctly.
Maybe see if a gold state appeared.
Oh yeah.
Not yet.
Okay, sorry. The ultrasound just needs a lot of jelly and fluid to work properly. Any air and it doesn't see anything.
We're not 100% sure yet that all of the coordinate transforms are correct.
Yeah, there's
So
definitely
there might be some room for improvement.
Can you use Vaseline?
So, sorry?
Never mind.
what top hypothesis do we have at the moment?
The mug.
Interesting. That's surprising. Yeah, it probably is the case that the coordinate transforms are totally right, because this should be doable for Monty.
Yeah.
We just have a few more, like a few more observations. Oh yeah, did we show the goal state? Sorry, if you go back. Do you see one?
Yeah, no.
Okay. Never mind.
Seems like the tracker
The
probe
tracker
is
is
not
very
calibrated
awesome.
right.
It's oh yeah. For what it's worth, that's just for the human. It doesn't affect the data collection.
Oh, there is a suggested pose up here. You want to have a look at it?
Okay, yeah. If you rotate, so yeah, I guess that was
Stick it in the
before
bag.
calibrating, so maybe it's yeah, really off. But anyways, you can see the principles operating as well as the coordinate transforms that are clearly still in need of debugging. How many steps are we on now? Okay, I'll try and be a bit quicker. You can kind of see on the ultrasound image, like at the top, these like zebra stripes. Like that's just one of the kind of artifacts that comes in, and we have to kind of.
Are those reflections or something?
Okay, there we go.
And we finished.
Yeah, it's kind of like bouncing back and forth and creating like a false image at a certain depth.
So what did it categorize? Monty's heart.
Monty's not.
Oh,
Oh, that's a shame.
oh well.
Well,
You
next
can try
time
multiple times, right? Or no?
we can try
multiple
another
back.
object. But maybe you first demo yours.
Yeah.
If you also get it wrong, then we can have a tiebreak object.
Right.
So
Gonna head downstairs to our setup.
maybe the last parameter changes didn't help.
Very strange.
Because we did have some, the late, it looked good when it was plotted, but yeah. We did recognize the objects in the data set we collected. So I guess this is the demo effect.
Because yeah, the dimensions are quite different for the hot sauce bottle, so it
Yeah.
should be quite doable,
Yeah,
even with noisy point normals and all that.
maybe we, for the next one, we remove that last change. Just to see if that maybe broke something. Sorry,
back
it's
up to
okay.
50.
This is your robot's camera?
No, it's not a robot's camera. We just got
Can you see it?
his laptop is blurring things.
Oh, it's because it wants to look for your blur the background.
Yeah. I'm gonna do another thing here.
Yeah, unfortunately, you don't keep doing that unless that's turned off.
No, you're
Yeah.
like it's for sure blurring the
I
background.
don't understand. Oops.
Yeah. So I'm joining with my phone and I'll do the same thing.
Recording in progress.
Yeah, for what it's worth, I think that setting, if it's on Zoom, it's under the video, the up arrow. On the bottom left corner, there's a setting called blur my background.
It's not blurred.
Oh,
Like this would be blurred. This is
oh, it's just, yeah,
focused or Apple is applying its own thing.
yeah. Then that would be the green camera in the top kind of menu bar. If you click on that,
That's the
Then-
reason.
Okay, I also did my phone view down here.
okay.
Oh, my phone died.
Oh, the demo gods are not nice.
Oh, there you go. That looks better.
Is it good? Okay. That's good. Okay.
Okay, okay, maybe it's focusing on me.
Yeah, that's the focus.
Okay.
Yeah, I'll stay
Nice.
here.
Could you put the phone on the tracker so we get like first person experience? I mean, wicked.
I didn't get it.
Yeah.
Okay, we need an object.
Yeah, it's the
Hot sauce, please.
same object.
Hot sauce. Okay. All right. Starting. What you're observing now is it's resetting into the starting position.
Oh, wow, already hot sauce, most likely hypothesis. It's impressive.
He also thinks it might be Monty's heart, so I don't know.
Oh,
Oh,
oh, it's neck and neck.
yeah.
And you
Okay,
can
hot sauce back.
Yeah.
Neck and neck with what? I can't see that.
No, now hot sauce is a clear lead, but there was Monty's heart as well there for a few steps.
Monty's what?
Oh,
The-
detected hot sauce.
Oh, wow, good job. That's pretty
Nice,
awesome.
nice.
let me share my entire screen actually, because that will be better. So pick another one.
Can you do the mug?
Yeah.
They already did the mug. Let's do something different.
Okay.
Spam.
Sorry.
We could do the bug and something.
Yeah,
our-
do this. You
ours
can do
are-
the spam.
Ours are pretty quick. Hold on, let me just turn off I wanted to share because I wanted also you see. There we go. All right. What's on the? Oh, okay.
Yeah, it's so beautiful.
All right, here we go. Again, it's resetting.
Oh, Terry, by the way, the spam can here is called potted meat can.
Oh,
the-
really?
Full name in the data set.
Oh, okay.
No product placement.
And by the way, you can see the models in the upper right corner of the visualization. Like that's all that Monty knows.
That's cool.
Very sparse. Interesting that it was sparse images.
Okay, it means between the two, they meant a mug or a potted meat can.
What's the back end for that visualizer?
You keep saying global matching step 33.
Oh, we didn't debug those logs.
Maybe it's
What's
Maybe
happening
upper
is
goal
the
state.
camera is above the object, so it wasn't getting any
Ah.
sensor input, so it was
Okay.
just bypassing the learning module.
Of
Okay.
object.
Oh, nice. There you go.
Whoa.
Boom.
Wow.
What else you want to identify?
How about the Numenta brain?
All right, this one is a little different setup. You have the platform.
I don't think this one works very well.
Do you have the platform? Okay. Yeah, it needs the top platform, right?
I don't remember.
Yeah, just put it on top platform. So we have an extra platform for this one because our sensor didn't go far enough to see it on the platform that we built. So and we
Yeah,
also
and presumably the platform is kind of part of the model.
yeah, although like we're not sure if this is the platform we used or if we used a different one. So we'll
Okay,
find.
cool.
So
Testing robustness.
yeah, so here you go.
This object is also very small, that the patch is sometimes just off the object a lot, and that's somewhat it doesn't work for that reason.
And hopefully it will not fling the brain off of the platform either. It's pretty light. We don't have many tolerances built in here.
A flying brain.
Yeah.
Oh, don't see Monty's brain in the hypothesis space.
Yeah. This one might not work. We'll see. Yeah, right now the sensor is above. So when you're seeing stuff like this, it's just not getting any data because, again, our policy is just purely random movements.
Also, the time flight sensor works best with shiny objects and objects that are not like metallic or whatever. They don't really give good data.
Oh yeah, sorry. Visualization.
Yeah, it thinks it's a tuna soup can. This is why it's causing the tuna soup can. Right.
Wait, tomato soup or tuna can? Tomato soup.
Sorry, tomato soup.
Probably,
Yeah,
think
I guess
the
that. So,
platform Probably. Okay,
but
can I
you know,
try?
you got an example of a failure mode.
What
That's
if-
not bad for the free.
Yeah.
Do we
Yeah,
get a
that's awesome.
second try on the spam can?
Yeah, what if we get the brain? No.
It's actually pretty good about the brain. You just put it on the bottom, right? Yeah, just normally. Yeah, I
Or the
mean,
heart?
the heart, sorry. Yeah. So it's pretty good recognizing Monty's heart. Then you can see the image of that's its model of the heart.
Yeah, wow.
That's pretty cool. Yeah, do you want to try the spam can again?
Yeah, should we try one more? Just
Just to
you change
hopefully have a
config back?
success. Yeah,
Okay. The checklist.
yeah.
Okay,
I would
so-
say the prize for highest actually definitely goes to you guys, but we just want to have a little bit of success.
Sounds
Oh.
good.
So-
Yeah, I'll stop sharing as soon as this completes.
So are you like in Monty, when you rotate, is it moving the agent around the circle?
Yes, it's we are faking it orbiting an object. There we go. Monty's heart.
So you're saying that this setup would be something that you guys actually will be using a lot in the future to do some of your testing?
Yeah, that'll be like a real world test bed for Monty.
And
Make one that's not made out of Legos. Something
we run it, test it.
and that way we can order one for each of us, and each one will have one at their homes.
You can probably point on the open space there. We're done. We're done with this demo. We're doing now.
We're gonna try and do the potted meat can. All right. If everything's better luck, get anything timed out. Who was gonna try?
So you can see the meat can in the bag. Niels can actually most of the time not see it because it's not see-through from the other side.
Okay.
Oh, yeah.
Calibration still looks
And
decent.
so here's a little screen, I think it's also being shared, where you can see how the tracker is moving in real time. And then the iPad screen seeing the corner of the can right now.
Maybe if we go to the hypothesis based screen, make sure we're getting images.
So yeah, you can see it does a decent job at extracting the patches and the curvature and point normal and all that. There'll just be a few things left to debug with the adding it all together.
What's in the back?
Spam can.
Spam.
Did you tell from the images?
Oh no.
Yeah, there you go.
Yeah, kind of.
Cool.
Yeah, there's the edge of the spam can here, I think.
What's the MLH?
Demented mug.
Okay.
You kidding me?
I think you guys overfitted on the Numenta mug. Just kidding.
So is the patch right in the center? The patch is being extracted?
Yeah, like this.
It's not always in the center. It's when it first finds
Oh,
when it first
okay.
finds the edge. So
gotcha. Yeah.
It felt we lost the tracker. 1 second while we
That'll,
rebuild the tracker
we need
system.
to we're better off not having it because it's if we want to continue, for instance,
okay.
because otherwise it's going to change the location. I think.
What did you use for the 3D visualizer?
Matplotlib.
Getting
Oh
that quick.
no,
The live one is V Python.
Okay.
The sensor location.
Yeah.
I think that's a vibe thing. Like it, yeah, part of the
Okay.
yeah.
Cool.
Oh yeah, here we go. Here's a good goal state. So right now the probe is over here and the goal state is on the other side. So the user actually moves the
Wow.
oh, okay, but the problem is we lost one of the trackers, unfortunately. But otherwise, basically, if we move it to a similar position, then in
That's really
unfortunately, the tracker, if the probe moves on this side now, we can
You
try
sure it won't get it?
and try. Maybe it's back.
Okay, there you go.
Okay, that's pretty close.
So, yeah, it's maybe if you rotate it, Will, so I can see. Okay.
So once it goes into the actual point,
Yeah.
the arrow
There you go.
disappears. So
Yeah,
you see
once
that. Got that.
once you
Oh, that's nice.
then the arrow disappears, and then if you keep doing inference and get another goal state, then what you call it, it'll do the same thing. It'll create a new arrow. Yeah, that's really cool. How many steps are we on? I'll just collect a few more data points, see if we can.
There's sort of like a can inside.
Yeah, I think we learned that you overinterpret a lot of stuff if you know what it is, but a lot of it is just artifacts.
What did it say?
Want to start?
Yeah.
Oh man,
What? Okay. Yeah.
worked much better earlier today.
Yeah, we made the fatal error of trying some last minute adjustments to things, and that may have thrown the system off. But
That's how it is.
if only we'd picked Monty's heart.
Yeah.
Clearly, we would have gotten 100% accuracy.
Number of steps higher. Yeah, this is the number of points that we collected just then, and the point normal pointing out from the object.
Nice. Yeah, and at least some of the learned, like we did for both the potted meat can and the Numenta mug, we scanned it with 200 points, and we've plotted those learned models, and they look decent.
Yeah.
But yeah, like right now, curvature information isn't used at all, really, and yeah, there's just like we're basically just matching the locations and a little bit of help, I guess, from the point normals. But
Nice. Ding.
Yeah. So now now we go to the scoring phase. I'm gonna stop sharing.
Is Terry sharing her screen now?
Well, we'll give
Oh.
Terry a few minutes to think. And then, yeah, I don't know, Harry, since you saw everything too and you're pretty independent, if you'd like to also score, I can send you a link.
okay.
Let me find
Can
it
you
again.
can you see the link filled out of mine?
Hang on. Yes, I can. Perfect. Yeah, that's great.
Okay.
You're gonna put it in chat to me?
Yes.
Do you
And
want me
then
to explain mine? Harry, use zeros for, or use O's for your choices.
and
Okay,
then
well,
yeah, Terry, go ahead.
okay, so I think now Harry probably might be a better judge than I am, but I'm basically going from my viewpoint, so it's pretty subjective. I understood more of what everything as awesome team did. I thought they had their visuals matched the image and the different perspective, the different angles. You could really kind of see how it was going around. I understood their explanation a little bit better. I thought their setup was a lot more condensed and easier to understand. So I thought that was easier on the eye. I do believe that it's not a tumor was a very impressive solution with regards to dealing with the sonogram and the difficulty of sonograms and the future capabilities of doing medical diagnosis remotely, around the world. That was impressive. The most ambitious, all of three were very ambitious, but I do believe that the Icarus had the most ambitious just because I don't think that they had the equipment that they needed to get further down with their project. I think if they had more of a sophisticated drone or whatever, their outcomes would have been a lot better. They spent most of their time just trying to get the setup, which kind of took away from the rest of their project. So I think their project was a lot more ambitious just because they didn't start with sophisticated enough equipment. I thought all of them, all of you guys ran into several different problems and hurdles to get over, and all three teams really kind of did extremely well on all of those. I thought, trying to come up with solutions and creative solutions. I thought you guys did, all three teams did a great job. Also with the team players, I think that's one thing with regards to Thousand Brains projects, you guys all work so well together. And I think everybody did their part and actually pretty much were a full part of each team and each team's project, which was nice to see. I think that everything awesome demonstrated that the Monty's capability just because they were able to detect, figure out what the item was pretty much on everything except for that brain, which was exciting. And I think all three actually gets me excited about Monty's future because all three of them have different applications that they can apply. Also, I think the awesome one is something that all three, the whole group can use in the future right now. So the benefits are short term of this project. And so I think probably I would award everything awesome the prize.
I think everyone will understand this decision.
Yeah.
Yeah. Yeah. Thanks a lot, Terry, for the great ranking. I would agree with all of that. And yeah, I think since everything is awesome is pretty far ahead in points, we don't even need to fill out this column because we can't catch up to them. Yeah.
Yeah. Altruistically fighting.
Yeah, but it's really impressive how much you guys, I mean, my brain hurts and I don't even understand 90% of it. So the 1% part that I do understand, my brain's exhausted. So I think you guys did a wonderful job, and it's so I just really enjoy watching your whole team work so well together and develop. I mean, these projects just in a short period of time. I think it's wonderful.
Yeah, thanks, Terry.
Harry, do you have anything to say?
I'll make a few comments. I did not take notes, so I can't fill out things at the level of granularity that you did, Terry. But I concur with the general sense that everything is awesome on the whole. Takes the cake and walks away with first place. I think, to me, what's most interesting to me is it's not a tuna, not a tuma, because I think that really shows how Monty could be used in very different real world applications, as opposed to the other two demos, which are more the classic, take pictures and see if you can recognize an object. Everyone's working on that. And that's fine, but I think the idea of dealing with ultrasound, its complexities, it's amazing that you got any results when you look at a sample image and the artifacts. Dealing with that just represents such a fantastic promise that I certainly hope that that's pursued in addition to the other sort of classic ones. I do have a question, or maybe it's an observation of my understanding of how these systems collect data and try to resolve it into a hypothesis. And that is, we do a very good job at understanding the world around us with one eye. Depth information from these devices is pretty crude, and I think that's a long-term feature compared to the resolution of the RGB camera. And I wonder if including the depth information actually makes the problem harder than working with just a 2D snapshot, but moving it around from all different perspectives gives you all the information you need, I think. And I'd like to have your thoughts on the pros and cons of using depth data, given the technology that is deployed in these two examples.
Yeah, I think definitely in humans, we have a bunch of different heuristics how we estimate depth, besides like binocular depth estimates. So I think it's still quite important in human vision to have depth estimates, and like we do it pretty early on in the visual system. But it is definitely not like as accurate as you would get with LiDAR or maybe even the ultrasound. So I think it's a bit of a mix of both, that you need some kind of estimate to be able to tell how far things are away from you, because otherwise you have no way of knowing like how big like a movement of your eye would translate to movement in the world that you see. Like an object that's this far away is much smaller than the same object when it's closer to you. But then also being able to deal with those just being pretty rough estimates, which right now we're, I guess, decent at, but not great. But yeah, so still necessary to a degree, but not to like millimeter precision.
Yeah, it's like in the everything is awesome case, the robot is only moving up and down. And I mean, the depth changes because like the object is, like it has shape, but the average depth is like, it's kept at a constant. For the ultrasound, it's kept, I guess, constant with respect to the bag that it is in. So again, there's not a huge depth value, like variation in the depth value, even if you get it. So I don't think depth in like those senses are like very useful. Yeah, I guess. So I think that's why like maybe you thought about it kind of that way. In our case, like it's very like if it were to like work and Monty, so if it emitted a motor policy, actually if we're far away, then it should emit a policy like get closer. In that case, having accurate like depth information will be like crucial, so that like one, it can, you know, get closer to the object of interest is trying to learn, and two, so that it doesn't also collide into the object. Like here, they're kind of like artificially like set up so that like there's not going to be a collision between the agent and the object that we're trying to identify. So like, yeah.
But yeah, I think that's also another good point is that like you don't necessarily need an entire depth map. It's more like, for example, in our ultrasound example, we're not using the whole kind of depth image we get. We're just using one depth value at the center of the patch, and then we're moving it. So that's kind of this approach of just saying, right, how far away am I from what I'm currently looking at, and then move around that to build up the model, but not actually requiring to get like an entire depth map and integrating that information. I don't know if that answered your question or matched your thought.
I think no, it does, but I still think that if you have the capability and the design to be able to move the sensor and orient it in any direction in space, then parallax information is every bit as good as
Oh,
depth
yeah.
information gathered from the image.
Oh,
And I
yeah.
just think that given
Right.
the resolution of those two different images, a depth map with today's technology versus the actual, 2D snapshot, I'm just suggesting you may be better off using the 2D snapshot and the physics of parallax to figure out what's going on. That depth
Yeah.
information is actually introducing noise, making it more difficult for you. But that's a hypothesis.
Actually, but I did try SFM. So because I took 12 pictures, you know, with, you know, overlapping, and tried to, you know, do 3D reconstruction from a bunch of 2D photos, right? That's using more of the triangulation that, you know, the technology that you're talking about. I think the problem was that the image, because there were a lot of backgrounds, the features didn't really match. Like there would be features from the floor and try to match feet, you know. So, you
That's
know,
right.
yeah.
But
So
one of the nice things, like at one point we were kind of reviewing different theories for how depth information first appears in the primate visual system, and you know it's probably something similar to, or you know, it definitely relies on parallax both with binocular and also with motion. But what's interesting is because again, Monty's a sensory motor system, the primates are sensory motor, and they kind of focus in on one area. In that setting, that actually solves a lot of the challenges that parallax faces in computer vision, where you're trying to match like thousands of points in these massive images. You know, it's computationally expensive. There's a lot of ambiguity. It's just interesting that, again, like just the kind of way our eyes are set up and everything solves a lot of that. And yeah, so it's something we don't have at the moment in Monty, but I think it's a great point that it would be, yeah, really interesting at some point to bring that in. Maybe the next robotics hackathon.
Yeah, I mean, I think intuitively one always thinks, oh, more information is better.
Right.
And I'm just, given the specific technology, wonder if that's true in this case. Obviously, in the long run, if you had very, very high resolution depth data, surely that will be helpful.
Yeah.
I have a funny story to tell you. When I first moved out to California, I worked for a company called Biometric Imaging, and it was run by a guy that's very well known in the Valley. He did spectrophysics, he did a lot of lasers, but he does mostly medical diagnostic. Well, just about 6 months ago, he contacted me because he saw my connection with Numenta, and he's from India. His name is Bala Manian, and he was when he was a child, he was in an accident and he lost one of his eyes. So he's always been wearing one patch. And so his question was, he was always wondering how could he drive a car when he only had one eye? And so he said, he told me that the Thousand Brains Theory plus another book about how do I invent were his two books that he kept on his desk all the time, and he would periodically just pick them up and read them again, because he feels that Thousand Brains theory is a strong thing to explain to him why he can drive with one eye, and really feels that it's a great theory. So to bring that up, I mean, when Harry said one eye, I said, well, I know somebody with one eye. And
Wow.
he
That's what
the
I was
same-
imagining, and it'd be very interesting. Wouldn't be surprised if there aren't research papers about how people with one eye navigate and what deficits they have or don't have.
Yeah.
Right. So it's probably been well studied, I would imagine.
Yeah, but he's a very interesting guy. If you ever want it, when you're out around, he would love to talk to anybody about it. He's very excited about it, but like I said, he does a lot of medical devices, and he's very in tune. He wants to see how possibly Thousand Brains. He's really into the gut and brain connection and the whole thing of taking into that information. But I thought that was kind of interesting, that the fact that he had the one eye and has that same question that Harry had.
Yeah, that's cool. Definitely be cool to meet sometime.
Hmm.
Yeah.
Yeah, he's a very smart guy. He would really, and he's quite a character. He's very entertaining.
Sounds great. I see, Tristan, you're awarding yourselves the trophies.
Everybody who hasn't seen these trophies that won as a result of the hackathon. So here you go, Rami.
Yeah.
Yeah, congrats. That was awesome.
Congratulations.
Awesome project.
Yeah, it was awesome.
Yeah. Isn't there a spare spam?
Yeah,
Exactly.
there's a spare spam can. Well, I was thinking the team that gets
Open one and enjoy it. That's your treat.
I mean, I think.
gonna hand this to Jose.
There aren't too many trophies that you can actually consume.
I'm not sure if there's actually still spam in there.
I hope
they
not.
filled it with something.
I know. I don't think there is. There's holes in them if it is. And I don't think potted meat is much of a trophy.